When you look at a chemical reaction, you probably just see chemicals and coefficients and an arrow. But there's a lot more to chemical reactions than just a balanced equation. For example, there are extremely slow reactions, like the changing of colors in the fall, and extremely fast reactions, like the burning of fuel in this space shuttle launch. The area of chemistry concerned with the speed of a reaction is called chemical kinetics. So in this video, I'm just going to give you a brief introduction to chemical kinetics. So we can apply it to looking at different speeds of chemical reactions, not just balanced equations and coefficients in chemicals, but really how fast are reactions taking place. So first of all, let's just take a look at what a rate is. Well, a rate is the amount of change in a given amount of time. And you guys use rates all the time in your daily lives. You just might not think about it. And what we're going to do is take a look at a couple common rates and dissect them so that we can apply them to chemical rates of change. So a rate of change that may be very common for you is when you're driving in your car, you're going in a certain number of miles per hour. So your speedometer says mph on it. And what the mph really means is it's miles. It's the amount of miles that you've traveled or the change in distance that you traveled over a certain amount of time, the change in time. So miles per hour. Another rate that you may be familiar with is the speed of your internet, so megabits per second. And if we break that down into a ratio or a fraction, we have megabits over seconds. And you can see that the word per kind of equates to that line in the fraction, so megabits per second or miles per hour. Now, another way we can write megabits per second, and this is going to pop up here and there when we talk about chemical kinetics, is we can write that as that unit as MB and then a little dot for multiply times seconds to the negative first. So we're going to see different ways of writing these rates and the time. One thing I want to do is point out what a chart would look like if we had a reaction. So we're going to make it the most simple reaction possible. A is turning into B, and we're going to say A, they're all the purple dots, and B are all the green molecules. So we start out with 50 molecules of A and 0 molecules of B. That's what we start out. That's before the reaction proceeds. And after 10 seconds, we are now down to about 23 molecules of A. So what happened, and the way we can write that, is we've lost 27 molecules. If we went from 50 down to 23, we lost 27 molecules of A in 10 seconds, in those first 10 seconds. And the negative symbol means that we lost that amount. Now let's take a look at B. B starts out as 0. We have 0 molecules of B, and we end with about 27 molecules of B. So what we have gained now is 27 molecules of B in 10 seconds. How can we get these two ratios to equal each other? Well, all we have to do is we have to put a negative sign in front of the rate of change for all of the A stuff. If we do that, if we put that negative symbol there, and we put everything in parentheses, put a little negative symbol in front of that whole thing, now those two ratios are equal to each other. And we can look at the arrow as kind of equaling each other. What we have here is what's called an average rate of change, because we've taken a certain amount of change over an extended period of time, and we've boiled it down to, okay, what is the rate of change in this period of time? The delta, the change in molecules over the change in seconds. This is an average rate. Another thing we can do is we can find an instantaneous rate. And the way we do this is by taking the slope of the tangent of the line that's tangent to the point where we want that instantaneous rate. So you'll see at the beginning, at 10 seconds, A is losing, you're losing A's faster than at the end because the line is sloped more downward at the beginning than it is at the end. At 30 seconds, our line is flattening out, so we're not losing A's as quickly. That's called an instantaneous rate of change. Now, up to this point, we've been dealing with losing 27 and gaining 27. And that's because our coefficients were both 1-to-1 ratio. We lost one molecule for every molecule of, we lost one molecule of A for every one molecule of B that was created. But what if we have coefficients that are not equal to 1? What if we have different proportions of coefficients? How can we write or represent the rate of change when the coefficients are not always 1? So let's write this chemical formula. We have hydrogen combining with iodine to give us 2 molecules of hydrogen iodide. So it's a 1-to-1-to-2 ratio. Now I'm going to write the rate, and I'm going to use the numbers that are given here in this graph. We're losing 28 molarity. So this is concentration. We're losing 28 molarity per 40 seconds. Okay, so the change in molarity over the change in time. On the other side of this, we're gaining 56 molarity for every 40 seconds of HI. So how are we going to make these things equal? We want to make these two relationships equal. Well, the first thing we need to do is we need to put a negative sign in front of A. That's what we kind of started out with doing on the previous set of information. Now, the second thing we need to do is determine how we're going to deal with this 56 versus 28. What we can do is we can multiply the right-hand side by 1/2. And that will make these two sides equal. So our ultimate goal here is to make these two sides equal to each other. So we can really kind of work on formulating an equation. Now, where did that 2 come from? That 2 comes from the coefficient of HI, or hydrogen iodide. So we're using those coefficients in our equation that we formulated to try to express rates of reactions, rates of chemical reactions. So here's the formal definition for a formula or an equation for determining rates of reactions. If we have this generic equation, A plus B gives us C plus D, the rate is calculated by taking -1/A, that's the coefficient lowercase a, and notice how all of the signs for the reactants are going to be negative. And that's because we're losing that amount of reactant. We're losing the reactant side, and we're gaining the product side, so the products should all be positive. So 1 over the coefficient multiplied by the change in concentration over the change in time for that specific chemical. And we can make all of these things equal to each other. So if we know one piece of information, we can really easily find all of the other pieces of information. So let's take a look at a practice question. During a thunderstorm, we have lightning, and this really happens. It turns to oxygen, it splits oxygen up, and one O2 molecule will then react and bond to one of the split up half O's, or half O2s, so one of the O's, and create ozone. So what's the balanced equation for this chemical reaction? So we have oxygen turning into ozone. Now if we're going to balance this, we're going to change our coefficients so that we have the same number of oxygens on both sides. So if we put a 3 in front of the oxygen and a 2 in front of the ozone, that gives us 6 atoms of oxygen on both sides. Let's write the rate equation for this. So the rate is going to be equal to, now the reactants, remember the reactants are going to be negative, 1/3. That's the coefficient of that oxygen. And we're going to multiply 1/3 times however much that oxygen, the concentration of that oxygen changes in a certain amount of time, in a certain change in time. So we're writing this equation. Now that's going to equal, the next one's going to be positive, 1/2. Now the 2 comes from the coefficient of ozone. So we have 1/2, that coefficient of ozone, multiplied by the change in the ozone concentration over the change in time. So all we're doing is kind of formalizing what we sort of tried to do on our own in the previous slides. So here is this official rate equation for this reaction. Now we can use it to solve problems. If oxygen is being depleted at a rate of 8 molar per second, what is the rate of ozone that's being formed? Well, what I can do is I can just substitute this rate in for my O2. So -1/3 times And the rate here is negative 8.0 molar per second. And the reason it's negative is because it's being depleted. We want these two sides to equal each other. So we kind of have that double negative on the left. That's going to equal 1/2 times whatever the rate that ozone is being formed. That's what we're trying to find. That's the x value. So if we're solving for x, we're going to take the left-hand side and multiply everything times the left-hand side. So we get 8.0 over 3, and the negatives go away, remember, and that is, in the units are molar per second, or m over s, capital M over s, and that's going to equal 1/2 times x. Now if we solve for x, we want to multiply both sides by 2. That gets rid of the 1/2 for us. So then x will equal 16m over 3s, because 8 times 2 is 16. And if we convert that to a decimal, what we end up with is 5.3 m per s, molar per second, and we'll keep that in 2 significant digits. So the answer here is 5.3 molar per second. That's the rate that ozone is being created when oxygen is being depleted at a rate of 8.0 molar per second.